Okay, we have a few more topics to go through to round out our whole titration problems in this chapter. What if we had a weak base titrated with a strong acid? You get a similar pH versus milliliters of acid added curve, just like with the uh, when we had a strong acid titrated with a weak base. We started higher pHs because it's base in the solution, and then when we're adding the acid, we get this curve. And note, it looks a lot kind of like the inverted weak acid strong base curve, where the base or the pH drops quite a bit at the beginning. It levels out to the buffer region, where you can get the half equivalence point, where you can get the pKa of the base, or the pK, and thus the pKb, and the pKb, and you go to the equivalence point like that. All right, what if we have a polyprotic acid? Well, if we have a polyprotic acid, we titrate with NaOH, such as, here's a weak acid, H2SO3. Note H2SO4, sulfuric acid, is a strong acid. This is H2SO3, a weak acid. Note if we add NaOH, we will snag one of these protons to make water plus NaHSO3, which still has a proton, so if we keep adding base, we will end up with Na2SO3. So we've got this first acidic proton that gets given up and this second acidic proton that can be given up. And since it's a weak acid, these two protons, excuse me, have two different Ka values. Note, Ka is from just the normal dissociation, so H2SO4, H2SO3 aqueous, in equilibrium with H plus HSO3 minus, that's Ka1. HSO3 minus in equilibrium with H plus SO3 2 minus, that's Ka2. And when you do the titration, hopefully you've been thinking you would get this. The pH, as you add milliliters NaOH, starts as a normal weak acid strong base titration curve until you get to the equivalence point of the first proton, and then the curve rises dramatically, pH rises dramatically, but it'll level out again into a second buffer region for this second reaction here, and then rise up again. So you've got your first equivalence point, your second equivalence point, the half equivalence point right here, halfway between the start and the first equivalence point, is going to be your pKa for your first proton. And between the first equivalence point and the second equivalence point, halfway in between there, is your pKa for the second reaction. Cool. All right. Now, here's the deal. If you don't have a pH meter and you're doing your reactions, and frankly, even if you do, we often put in indicators to tell us when we've reached the equivalence point. You've probably done it before in Gen Chem 1 where you used a phenolphthalein with your acid-base titrations. And if you recall, phenolphthalein is colorless when the solution is acidic, but it turns pink when a solution is basic. So let's look at these indicators. Indicators are just molecules that have different colors at different pH values. And so if you're having pH changes, that means you're having protons either going on or coming off. Turns out indicators are all weak acids, where if you have the indicator with the proton on it, you add water, it will dissociate into the indicator without the proton on it, an H3O plus, just a standard weak acid dissociation. However, it's a weak acid, so this equilibrium lies way to the left. It just turns out the indicator with the proton on it is a different color than the indicator anion without the proton on it. However, since it's a weak acid, this equilibrium lies way, way to the left, so it's mainly this color here, or it might be colorless. All right, the nice thing about these indicators, we choose molecules that are very intensely colored. Just a little bit of molecule will provide a lot of color Therefore, we're not worried about adding, when we just add a little bit of this indicator, we're adding a little bit of acid, but it won't affect anything because it's so intensely colored, we're not adding hardly any of this indicator at all, but we'll still see quite a bit of color change. And to finish this off, I'm going to go to your textbook now because they've got nice colorful pictures and stuff like that. So here's an example of our phenolphthalein, a very common indicator. And, well, once you get to organic, you'll understand the structure a little bit better. Here's the structure of it. But this form has a different color than this one. This, in acidic solution, this is colorless. But if it turns basic, the protons leave up here. And then we get this beast here, which has a pink color to it. And when you take organic chemistry, we actually show you why this doesn't have color and why this would be expected to have some color to it. And here is the color at various pH values. Note that you aren't going to get this molecule with the protons not on it until you get to above a pH of 8. But it's tough to see. If you look closely in, if you get your textbook, you'll see this pH 8 has a slight pink color to it. And so in our titration curve, it will be colorless because of the colorless form until we've had enough base to take off the protons, and then it turns a little bit of pink because we're halfway. Some of the molecules are colorless, some are pink, about 50-50, and then we've got them all in the basic form. It's a dark pink, which means if you're doing a titration with phenolphthalein, you want to stop when it's just the faintest pink. When it's just the faintest pink, at that point, we know we're at a pH slightly above 8, which is a pH value you normally see when you're titrating weak acids and strong bases. That's a normal pH around 8 to 9 that you will see at the equivalence point. Okay. But the question is, what if you want to try titrate it to different equivalence, or your acid has a different equivalence point? What if the pH is 2 at the equivalence point? What if the pH is at 11? Well, we can use these indicators, and we can actually, with a bunch of different indicators, figure out what the pH of a solution is just by throwing an indicator in there. So if you had, say, an extremely acidic solution, you might want to throw a little bit, put a drop of crystal violet in there. And if you add crystal violet, if the pH is around 0, you'll see that it is yellow. If the pH is around 1, it's green. If the pH is greater than 1, it's kind of blue. So all these different indicators, they turn different colors at various different pH values. So the reason we choose phenolphthalein, which is down here, is because most weak acids at the equivalence point have a pH of around 8, so we want the color change at a pH a little after 8. Okay. Another indicator that you could use would be Thymol Blue, because it also, even though it has two different, check this out, it has two different pH ranges. So if you start in your solution at a pH of 1, it might be red, and then change to kind of a yellowish color. But then as you get close to pH 8, where you're going to find most of your weak acids change to the base form, it'll turn from yellowish to green to blue. I had a student one semester who was red-green colorblind. So phenolphthalein did nothing for him because it was colorless no matter what. Even though it was bright pink to everyone else, he couldn't see red, shades of red, so it was colorless to him. So we used Thymol Blue instead, and he couldn't see the green. So for him, it was either yellow, yellow, and then it turned blue. He actually did really, really well on titrations with Thymol Blue because he could really see that color change from yellow to blue. Couldn't see the green and couldn't use phenolphthalein at all because he couldn't see the red. But we have all these different indicators, and they're different colors. If you've ever used special indicator paper where instead of litmus paper, blue and red litmus paper, we have universal indicator paper where it's kind of this orangish color, and you just put a drop of your solution on it, and then by the different color the paper turns, you can tell what the pH is, because it's a combination. It's a combination of various indicators on there that are put on there not to interfere with each other, but give you a definite color at certain pHs. All right. Well, good news. That's the end of our titrations. Even better news, that's not the end of the chapter. We will continue on with the solubility equilibria in our next video.